All right, welcome. In this explainer, we are going to tackle a really critical question in machine learning. Okay, so let's just dive right in. We've all been there, right? You build a model, it performs perfectly on the training data, and then you introduce it to the real world, to new, unseen data, and its performance just tanks. It's this huge gap between the training and test results, and today we're going to unpack exactly why that happens and, more importantly, what we can actually do about it. Yeah, that discrepancy, it has a name. It's called the generalization gap. And the root cause is a really common problem called overfitting. Honestly, this is the central challenge we have to solve if we want to build models that are, actually useful out in the wild.
And this really gets to the heart of the problem. On one hand, you've got this amazing high accuracy on the training data. That's all the stuff the model has already seen and studied. But on the other hand, performance just plummets when it faces new data. It's like the model absolutely aced all the practice tests, but it's completely bombing the final exam.
So, what's really going on here? The crucial thing to understand is that the model hasn't truly learned the underlying patterns in the data. Nope. Instead, it's just picked up on all the little statistical quirks and noise that are specific to the training examples. It's effectively just memorized the answers instead of learning the concepts.
This analogy just nails it, doesn't it? The analyst can recall every single detail from the past but has zero ability to predict the future. So, what do we do? How do we actually fix this? How do we build models that learn instead of just memorize?
Well, the answer lies in a whole toolbox of techniques called regularization, and we're going to walk through 4 major strategies today. So let's start with the most direct approach, basically adding constraints right into our model's training process.
And that brings us to our first strategy, explicit regularization. The core idea here is pretty straightforward. We add a penalty to the model's loss function to basically say, hey, don't get too complicated. Okay, so a super common way to do this is with something called L2 regularization, or you might hear it called weight decay. What we do is add a penalty that's based on how big the model's weights get. It's essentially telling the model, keep your parameters small. And by doing that, we force it to find simpler, smoother patterns, instead of trying to chase down every little bit of noise in the data.
So what does this actually look like? Well, if you use a really small penalty, or low regularization, the model has way too much freedom. You can see it fits the noisy training data perfectly, creating this jagged, overly complex function. This is like textbook overfitting.
But now look what happens when they apply a moderate penalty. The function starts to smooth out. See? The model is now ignoring some of that random noise and is really focusing on capturing the true underlying trend. This right here, this is the sweet spot we're aiming for. This is a model that can generalize. Of course, you can take it too far. If we crank up the penalty way too high, the model becomes too simple. The function gets so smooth that it completely misses the main trend. This is the opposite problem, and we call it underfitting. So the key, really, is finding that just right Goldilocks balance. So constraining the model's parameters is super powerful, for sure. But it's not the only trick we have. What if we could build safeguards directly into the training process itself?
And that question leads us right into our second strategy, implicit regularization. So instead of explicitly adding a penalty, we're going to change how we train the model. And one of the most popular and, honestly, effective ways to do this is a technique called early stopping.
The logic behind this is it's beautifully simple. You watch how the model is doing on a separate set of data, a validation set. In the beginning, the model gets better on both the training and the validation data. But then you hit a point where it starts to overfit. The training score keeps going up, but the validation score starts to drop. And that's our cue. We just stop the training right there, at its peak performance, before it gets a chance to start memorizing all that noise. Okay, so far we've been all about tweaking the model and the training process. But what about the data itself? Shouldn't we look at that? Turns out, shifting our focus there can be one of the most powerful things we do. And that brings us to our third powerhouse technique, data augmentation. Think about it. If overfitting happens because the model is memorizing a limited set of examples, well, the solution is pretty obvious, right? Let's just give it more examples to learn from.
The idea here is so cool. We create new, synthetic training examples just by tweaking the ones we already have. So if you have an image, you can flip it, rotate it, mess with the colors, or even just add a little noise. The model gets to see all these different variations, and it forces it to learn what features are actually important. This makes it way more robust when it finally sees brand new data.
Now, data augmentation is fantastic, assuming you have a good amount of labeled data to start with. But what if you don't? What happens in those situations where getting those labels in the first place is the biggest headache?
Well, our final strategy tackles that problem head-on. And honestly, it's one of the most exciting areas in all of AI right now. It's called self-supervised learning. And the whole idea is to let the data, well, supervise itself. So let's break that down. You know how in traditional supervised learning, you need a person to provide a label, right? Someone has to tag the photo and say, this is a cat. Well, with self-supervised learning, the model is smart enough to create its own labels just by looking at the structure of the data.
Okay, but how does that even work? Basically, the model learns by solving a kind of puzzle that we create from the data itself. We call it a pretext task. For instance, we could just black out part of an image and challenge the model to fill in the missing piece. Now, to do that well, the model has to learn about textures, shapes, objects, all on its own. No human labels needed at all. And this is huge because it means we can pre-train really powerful models on massive amounts of unlabeled data.
So, at the end of the day, what's the big takeaway? It's that there's no single magic bullet here. If you want to build truly robust models, you need a whole toolkit. You've got to combine these strategies. Use explicit regularization to add constraints, train smarter with implicit methods, beef up your dataset with augmentation, and tap into all that unlabeled data with self-supervision.
And all this progress leaves us with a really fascinating big-picture question to think about. As our models get better and better at generalizing, are they just becoming incredibly sophisticated pattern-matching machines? You know, just statistical parrots that can mimic things without any real meaning? Or are they actually taking a small but very real step towards something like genuine understanding?
Hey, thanks so much for watching. If you found this explainer useful, it would be awesome if you could like, share, and subscribe. It really helps us create more content just like this.